In this recording, we're going to look at our second cubic polynomial. This one is already fully factorized. That means we can read off the x-intercepts immediately as -1, 2, and -3. Let's start the sketch by putting those intercepts on. Without fully expanding the polynomial, we can see that the highest power is x cubed, and its coefficient is 1. From that information, we can deduce that when x becomes large and positive, far to the right on the graph, y will also get large and positive. Similarly, when x becomes large and negative, far to the left on the graph, y will also become large and negative because -1 cubed is -1. We can start to draw that behavior and in fact connect the cubic up to the first two intercepts, one at -3 and one at 2. So it looks like this. The graph is started. We know that a cubic in general will have a maximum and a minimum. So the maximum must follow after -3 and the minimum must come somewhere before 2. By the time x reaches -1, the graph should have turned over its maximum and be coming down again. Then it will turn round and go up to 2. Roughly speaking, it should look like this. One further piece of information that we can put on very easily is that y-intercept, where the blue curve crosses the y-axis. That should be the constant if we expand the brackets for y. We don't have to do that expansion fully. All we have to do is multiply the three constants together. That will be the constant term, because that's what happens when x is 0. The product of those three constants in the brackets is 1 times -2 times 3, which is -6. So perhaps I should have drawn my blue curve a little bit lower so that it hits the y-axis at -6. We've not done too badly. We've got the general shape of the curve, but there is still some information that we haven't put on properly. For one thing, I've guessed where that minimum will be. Will it be to the right or left of the y-axis? We don't really know. And at the moment I've drawn the maximum halfway between -3 and -1. That's really just a prejudice. I've no reason to believe that it should be exactly at that spot. When we were investigating quadratic curves, we had some means of identifying where the turning points would be without using any calculus. We could use symmetry and horizontal shifts. Unfortunately, we don't have such methods available for the cubic. It just doesn't work. There is, however, a means of approaching this problem without using differentiation. Look at where the blue curve passes through the y-axis at -6. The way I've drawn it, the minimum is to the right and the curve is progressing downwards through -6. Imagine if that minimum was to the left, like this. In that case, the curve would have to be progressing upwards through that point at -6. If we look at the value just to the right and just to the left of -6, we'll be able to decide whether the curve is heading up or down. To do that, we have to do a bit of algebra. On the y-axis, x is 0. Very slightly to the right of the y-axis, x will be a small positive quantity. Slightly to the left of the y-axis, x will be a small negative quantity. We often reserve the symbols epsilon and delta for small quantities. I'm going to set x equal to epsilon in our formula and assume that epsilon is small. For very small quantities, the square and the cube and higher powers will be much smaller again. So compared to the original quantity, we can ignore them. Epsilon squared and epsilon cubed are much less than epsilon. We write statements like that with these double inequality symbols. They mean much less. That means that if we expand our brackets for y, we can in effect drop all the terms containing epsilon squared and epsilon cubed. They will be so small we can ignore them. Let's go back and do that. Here is our y, remember. Let's substitute x equals epsilon into that formula and then expand it. Clearly the constant term is still minus 6. I haven't bothered to write out the squared and cubed terms because I know that I'm going to neglect them. So the only work I have to do is to think about the linear terms in epsilon. Those will arise from the three brackets when epsilon multiplies the product of each pair of constants. So there'll be epsilon times minus 2 times 1. That's this combination, minus 2 epsilon. Then there will also be epsilon times minus 2 times 3. That's this combination, which comes to minus 6 epsilon. And the other one that's missing so far will be epsilon times 3 times 1. That's 3 epsilon. We can now collect terms, and we have an approximate expression for y, which is valid close to the y-axis, where x is 0. It simplifies to negative 6 minus 5 epsilon. But now that's exactly what we want. When epsilon is small and positive, we are just to the right of the y-axis, but y is a little bit less than minus 6 because we're subtracting 5 epsilon. That means the curve has gone downwards to the right of the y-axis. On the other hand, when we're just to the left of the y-axis, epsilon is small and negative. Since epsilon is small and negative, minus 5 times it becomes positive, and so now we are a little bit higher than negative 6. So to the left, the curve is above. That means it's still coming down as it passes through the axis. We can draw that now. That also means that the minimum must be to the right of the axis. Well, I can't really say much more about where that minimum is without doing some calculus, but at least we've now got it on the right side of the axis. The other question I raised was whether the maximum is at or close to the midpoint between negative 3 and negative 1. In other words, at x equals negative 2. We've no reason to expect that it should be at negative 2, but we can find out and draw it the correct side by doing a similar analysis to what we've just done with the epsilons. I'll need to wipe out the working that I've done above. It's going to get in the way when we draw the curve anyway. I've also restored the x's instead of epsilons in the cubic function. What actually is the value of y when x is negative 2 at that midpoint? That's easy, we can substitute it in. When we do the arithmetic, we get the value plus 4. When x is negative 2, y is 4. So now we just need to find out whether x to the right of negative 2 causes y to be a little less or a little higher. Similarly to the left. So we could choose x equals negative 2 plus a small quantity epsilon again. We can substitute that value of x into the expression for y and expand, again omitting the squared and cubed terms. I'm running out of space, so I'm going to move down to do this. Try to remember that expression for y. You can always scroll back and look at it again. And we're going to put x equals negative 2 plus epsilon in there. Here's the raw substitution, and then we can simplify this before expanding the brackets. Like so. The constant term will be 4. We know that already because that was what happened when epsilon was 0 and x was negative 2. So now, ignoring squares and cubes of epsilon, we just need to look at the linear bits. Again, that's each of the pairs of numbers times an epsilon. So the first term might be negative 4 times negative 1 times epsilon. And then there will be two other combinations. Here's what it looks like. It simplifies to 4 minus epsilon. We're almost there. We just now have to consider what happens for epsilon positive or negative. If epsilon is positive, that's to the right of the midpoint negative 2, but the y has come down a little bit. It's a tiny bit less than 4. Similarly, to the left, epsilon is negative, and there are now 2 minuses, so y is a little bit bigger than 4. That means that the maximum is not at negative 2, but the curve is descending through that point. If the curve is descending there, the maximum must be to the left. We won't be able to say exactly where it is without doing calculus, but we are now ready to produce a reasonably accurate sketch. Let's go back and finish the drawing. That's really about as far as I can get with this sketch, unless I use some differentiation techniques to locate the maximum and minimum. So that's where I'm going to stop.